Now we'll start our last lesson of the course with a quote from Nobel Prize winning physicist Niels Bohr. Prediction is very difficult, especially if it's about the future. And actually, speaking of the future, your AP test, you're probably not going to have to do any of this, but I'm going to go ahead and go over it anyways. So when we predict something, we can predict for an average or for an individual. But it's going to be the same either way, because if I say, if I'm rolling a die and on average, for some reason, I'm getting threes, that's what I will get. I predict my average will be 3, and I predict that any individual roll will be 3. So both intervals take the form where you have your average plus or minus, your critical value, or your, which in this case is a t-value with n minus 2 degrees of freedom times the standard error. Now, the standard errors are actually different for both, because if I'm talking about a mean or an average, remember those distributions tighten up with the larger sample size. When I'm talking about an individual, that will have a larger standard error. And here are the formulas for both, but you really don't have to memorize them for your AP test. And you'll notice the only difference between the two formulas, you have your standard error for slope times the difference between your x value and the average x value squared, plus the S of e squared, which is s on your calculator, by the way, divided by n. And the only difference is that extra term right there when I'm talking about an individual. So my standard error is going to be larger. And that kind of makes sense, because if you look at the data plotted for linear regression, you're going to expect the average to hug this middle here. And this shows the confidence interval. The green line shows the confidence interval for the average or the mean. The dashed line shows the confidence interval for any individual reading. So you can see that's much wider because we're trying to capture all of these points instead of just the averages of these points. So we'll do a quick example here. I'm going to do a 90% confidence interval. This is problem 14a in your book, so you might want to refer to it. I'm pulling the numbers from the book. So I'm finding a 90% confidence interval for the mean SAT math score for all students with an SAT verbal score of 500. So we have the slope, which for our correlation between verbal and math, and our intercept, which I'm pulling from the book. And so I just go ahead to predict the average. I put in the values for slope. The 500 goes here, and there's my y-intercept, and I got 547.0195. To do the interval, that y value, I'm going to do plus or minus my critical value times this crazy thing right here. And so my x of e, which I'm going to need there, that's 500. So that's the value I use for my prediction for x. And then I pulled this off the reading. If you look at it, look under, it's under the verbal math in the two readings, and then you have dependent variables math. Under r squared, it says s is 71.75. Next thing is I got the average by looking at the two rows for verbal and math. And if you look at the mean, for verbal, it's 596 point, and it says 296 in your book and 292 right here, but it'll be close enough for our calculation. And then finally, the standard error for the slope is down by the coefficient. So it's the third column where it says SE, or standard error of the coefficient, 0.0568. Put all these values in, and I get my confidence interval for the average math score, or the mean math score, for students who have a SAT verbal score of 500. Now I can also do it for an individual, so I have slightly different numbers now. The slope's the same and the intercept's the same. But now I'm doing a 90% prediction for an individual and who scored 710 on the verbal section. So now I have 710 here, which changes my predicted value. And I still pretty much have these numbers that are still from the table from before. So now my formula changes only in that I'm going to have this extra term right here. I substitute all of that in, and that gives me this confidence interval. So some things to keep in mind of what can go wrong. Don't use a linear regression when the data is not straight. Keep an eye out for plot thickening. If the spread changes with x, then predictions are going to be good for some values of x, but not others. Check the histogram and the normal probability plot of the residuals to make sure the errors are normal. I also like to check the box plot, well, for the data, not for the residuals, to check symmetry. Watch out for extrapolation. We cannot go beyond. So, for example, if I did the last problem from the previous video with the long jumps and said, oh, I want to predict what long jumps will be in 2000, 2012, and all that, I would be extrapolating. I'd be going outside of the range of data. And careful for high influence points and outliers, and also watch out for one-tailed tests. When you're doing the calculator, you can specify a one-tailed test like beta is greater than or beta is less than. But if you're doing software, it basically just does beta doesn't equal to, and that's a two-tailed test. And that brings us to the end of our statistics class and your new material.